Hi, in this video I will be showing you an example of a two-span composite precast concrete bridge. This bridge will have the W11 beam with a concrete deck on top of it. There are parapet beams at the two edges, and we'll have the central supports composed of two piers, and then at the ends we will have the abutments fixed to the deck. Now let us see the details of the sections in the AutoCAD format before going to the modeling process. So that's the cross section of the typical deck section. As you can see here, it's a 10-meter wide section, deck section, and you have W11 beams. The center to center distance between the beams is 3 meters, and you have 1.5 meter wide verge or footway at either ends, and then you have a 500 millimeter wide parapet beam at the edges. Let's see the the elevation. So that's the abutment on the left, and then you have the precast beam with holes driven in it for the dowels connecting to the end diaphragms over the abutment. Then you have a central diaphragm with, again, you have holes on the precast beam connecting to the central diaphragm. Then there is a crosshead. The diaphragm rests on top of this crosshead, and the crosshead is supported by pier columns. A typical section of the pier columns is shown here. That's an octagonal column section. The height of the abutments and the piers will be around 5 meters, and the length of, or the span length of, a typical precast beam is around 30.5 meters. And we will have pre-stressing applied to this bridge when we will see the modeling of the bridge. The pre-stressing is typically applied as pre-tensioned strands with a load of 200 kilonewton at each pre-stressing strand. The concrete class for the precast beams will be C50, and the rest of the concrete elements, that is the deck, the parapet beams, and the abutments and piers, they will be C40 grade. We also have some debonded tendons at the bottom fiber of the precast beams, and the length, debonded length, is shown in this diagram here. So they are varying lengths, and we will incorporate them in the modeling procedure. So without any delay, let's start the modeling for this bridge. So I've opened up the blank Midas Civil file. I'll click on this option for new project. Okay, so here I have the blank Midas Civil window. I'll switch to the top view, and we'll start by creating a node. So that's 000, apply, and we have a node here. Then we will extrude a main or longitudinal beam out of this node. So select all, we'll select this node, and I'll type in the distance by which I want to extrude. So I'll put in unequal distance, and in the X direction I'll say 30.5 meters, which is the length of one precast beam, and then we have a gap of 0.5 meters, and then another precast beam 30.5 meters. and say apply, and switching back to the top view, and you can see the lines have been modeled. Now I will copy this on the Y direction to get the other precast beams and also the parapet beams. So select all again, and this time using the translate elements feature, translating with unequal distance in the Y direction. So we have 1.5 meters, that's the distance between the edge parapet beam and the external precast beam. And then we have two precast beams separated by 3 meters, and then another parapet beam separated by 1.5 meters, and click apply. So that's what we have got here. Now we will be doing a grillage analysis for the deck, so I will create the transverse grillage members. So I'll go to create elements and just create an element like this, and we'll copy this to the other side. So using the translate function again, and this time equal distance, X direction, typing in 1 meters, and number of times is 30 meters, and making sure that I check on intersect node and element, so it will automatically intersect the transverse beam at all the longitudinal beam intersection points, and apply. So that's copied now, and we'll create another one over this side. So I'll try to keep this bridge as symmetric as possible. So I'll create another one over this side and translate, and this time -1 and 30 meters 30 times, and we'll select that transverse beam and say apply. So that's modeled now. Now there is also a central diaphragm over here, so I will go to create elements and we'll model the central diaphragm like this. So by default you can snap at the midpoint of a given element, so I'll snap at the midpoint here and snap here. That gives me the diaphragm, the central diaphragm over here. And now I will create the abutments, the crossheads and the piers. But before going to the modeling of those elements, let us first define the sections and materials for the deck what we have got here. So for the sections, we will start with first the W11 beam section definition. So the W11 beam is a special beam which is the product of Banneger concrete. So that W11 beam we will bring in from the AutoCAD file. Just to show you how the import can take place, I'll open up an AutoCAD file which has the skeleton of that section. So that's modeled with all lines. So if you have a polyline, you just use the explode function here, select everything and use the explode function to simply break it into lines. So they are right now they are all broken into individual lines, and save this as a DXF file. So make sure this is a DXF file, not a DWG file. Then we go to tools and we go to section property calculator and make sure the length units are same as the AutoCAD length units. So click OK and then go to file import from AutoCAD DXF and select the AutoCAD DXF file and click OK. Click yes, and that's your section here. These are only lines now. So now I will ask the software to create section properties out of these lines here. So section and generate, and we'll make a solid section, so plain type, and select all the lines here and enter a name, say W11 section, then calculate properties now and apply. So that will quickly generate the properties of this section, and you have a dot marked here that represents the centroid for this section. To list out all the section properties, just to have a check, we can go here and say list section property, and it will show us all the section properties for this particular section. Okay, now we will export this section back to our analysis package. So export, select Midas section file, click on this box here and say section for analysis, okay, or give it any other name, save, and click on the section, click apply, close, and I don't need this this file anymore, so I'll just say no. Okay, just in case I'll save this model as well, so you should always keep on saving the model from time to time so that you don't lose any data. Now we go back to properties and say section properties and say add, go to the pre-stressed concrete type of section, PSC, say PSC value, and I'll type in the name, so this is W11B. Import from section property calculator and click on the section which you just created, open and click OK. So here you have all the section properties and the section shape included in the main model. Now you can change in the properties. If you expect some cracking in the section, you can change them here. You have to input some parameters for the design based on this diagram here. So the software also does the design of pre-stressed concrete sections. So this is for that purpose. This particular data will not be used in the analysis, the T1, T2 and PT and HT, but I'll just enter some values here. So typically the thickness of the web and flange in this particular section is 0.17 or 170 mil, and the width of the section is 1.5 meters and height of the section is also 1.5 meters. Thickness for torsion is the total thickness of the webs, so that's 0.34. And now here I give the positions where I want to calculate where I want to do the stress checks. So I can input any position. These positions are measured from the bottom fiber. So I say 1.4, so it draws a line here, and the stresses can be calculated at this line. And I can also give another one here, say 0.2. Okay, and this default one is at the centroid, so I'll just say auto calculate the shear and the perimeter of the shear stresses at this at these sections, and click apply. So this particular section gets applied here. Now we are doing a grillage model, so the sections should be composite with the deck. So I'll use the composite section to create a deck on top of it and include the deck as well in the section properties. So select composite PSC, I'll give it a name, say composite section. Slab width for one particular precast girder that is effective slab width. I'll take it as 3 meters. Number of girders is 1, 3 meters, and 0.2 meters or 200 millimeters is the thickness of the slab. And now here I'll specify which precast beam I'm referring to, so that's W11. Click OK, and from the material I'll select the material for the slab and the material for the girder. So for the slab it is C40, for the girder it is C50, and click OK. Now the elements are normally referenced as the centroid. The element line is always referenced as the centroid of the section, but for the purpose of analysis and applying the loads, we would want the deck to be at the top always. So I'll change the offset for the section and make it center top, so that now the element is referenced by the center, is by the top fiber of the deck. And if I click on show calculation results, it will show me the properties before composite, that is due to the precast girder, and after composite, that is including the deck as well. So close this and click apply. So I've got the composite section. Now I will add some other sections. So I'll start with the central diaphragm. And that's a rectangular section. Height is 1.7 meters and the width is 1.5 meters, and that is also center top. Okay, and apply. Then there are the end diaphragms. And the end diaphragms are 1.7 meter in height and 1 meter wide. Apply again center top. Then we have the transverse grillage members. So transverse and transverse grillage members are also center top, and the thickness, the height will be equal to the thickness of the slab, so that's 0.2, and we have kept a spacing of 1 meter for the transverse members, so the transverse sections will also be 1 meter wide. Apply. Then we'll model the parapet beams as well. So we have two parapet beams. So parapet 1, parapet beams are 0.5 by 0.6 meters, 0.6 meters in height and 0.5 meter wide, and they will be referenced with the left bottom or the right bottom fibers. So I'll change this to left bottom and click OK and apply. Then parapet 2, this one is right bottom, so right bottom here, and click OK and click apply. Then we go to the substructure, starting with the crosshead. We have a crosshead that is 0.5 meter deep and 1.5 meter wide, and that's center top. Okay, and apply. Then we have the pier columns. The pier columns are octagonal section, and they will be modeled as the octagonal section. So the height is 0.9 meters, 1.6 meter wide, and then we have haunch in the section 0.3 meter and 0.2 meter, and that is center. Okay, and apply. And then finally we have a strip footing at the base of the abutment. So strip footing that is a solid rectangular section, center, and 1 meter deep and 4 meter wide, and click OK. So we'll use these many sections for our model. Then I'll quickly define the materials as well. So I'll go to material, add, and starting with concrete, the deck is C40. Now what we will do is we won't be defining any density for the deck. We will apply the deck self weight as a wet concrete load before the concrete becomes composite. So in the analysis we will be looking at the stage by stage analysis, that is what are the results before the deck is made composite, and what are the results after the deck becomes composite. So we will apply the weight of the deck on the precast beams when it is not composite with the precast beams. So that's why we are trying to keep the material density as 0, so that it is not considered automatically, and we have to manually assign the self weight of the deck. So I'll change the name as deck here, apply, and then I'll model the other materials. So for the rest of the structure we have C40, apply, and then for the precast beams we have C50, apply, and then we have steel tendons. So we will be using 15.7 millimeter dia strands. So I'll use the highest tensile strength strands from here, and click OK. So now we have got all the materials and sections we are going to use in the model. So the only thing now remaining to be assigned or defined in the properties is the thickness. So the thickness will be used for the abutments, because abutments we will model as plate elements. So I'll add the thickness, and that is 1 meter thick. Click OK and close. So I'll close this now. As you can see on your model view, we have all the sections assigned with the material 1 material and section 1, and we don't want to do that. We need to correctly assign them now. So we will use a simple drag and drop feature in Midas to assign correctly the material and the section properties. So I'll change back to the wireframe view by clicking on this button, and first I'll start by selecting the precast beams. So selecting all the precast beams, which are the central beams, and drag and drop C50, double click on C50 again, and drag and drop the composite section. Now I will change the transverse beams into transverse sections. So what I'll do is make the selection filter as Y from here, and select all. So that will select all the transverse members, all the Y direction members, and drag and drop transverse. Double click on transverse and drag and drop deck, making sure that that is deck material. And I'll now switch this back to none. Otherwise, you will always keep on selecting the Y direction members. Okay, now we'll modify the transverse properties at the ends, because these are not transverse elements but these are diaphragms. So these are the end diaphragms. So drag and drop end diaphragms, double click on end diaphragms and making sure they are C40 material. Okay, then we do the same here for the central diaphragm. So we select the central diaphragm member and drag and drop central diaphragm. double click on center diaphragm and drag and drop C40. So for each element we need to make sure that we have the correct material and correct section properties assigned. Okay, then we have got the parapet beams here. So I'll just select one of the parapet beams and make it parapet 1, another one here and assign parapet 2. Let's check the sections by clicking on the hidden view and switching to the side view. Okay, so we have got the, let's check from the bottom. We've got the sections correctly assigned except for the parapet sections. I'll show you why. I'll inactive the end diaphragm, so inactive, and let's see from the side view. Okay, so we don't want the parapet to be on top of the inside this this line, so we want it to be exterior to the slab so that the dimensions meet accurately. So what I'll do is double click on parapet 2 and drag and drop parapet 1. So shift it this way and select this parapet, drag and drop parapet 2. Okay, now we need to shift them downwards, both of them, because the offset we specified for the parapet was center bottom, which means the bottom left bottom and right bottom, sorry, and which means the left and right bottom corners are now in represent the reference line. So I will shift the offset slightly so that it meets exactly at the deck level. So I'll go to right click, go to parapet and change the offset to user defined, say 0.2 meters, click OK and click OK. So that's shifted downwards. Repeat the same thing for parapet 2. So 0.2 meters, OK, and click OK. So that's done. Now we have all the section properties in there. Okay, now I will activate everything. So that's this button will activate or bring everything into the display. Okay, now just to make sure that the parapet have the correct materials, I'll just select both of them and say select and drag and drop C40 just to be sure we didn't miss anything. Yep, it seems everything is defined here, and now I'll change back to the wireframe view and we'll start modeling the substructure. So let's start with the abutments first. So I'll select the elements here and here, and we'll create plate elements vertically. So for the plate elements, I'll go to node element, extrude, line to plate, and we won't we'll check off the remove option, otherwise what will happen is the source line, which is the diaphragm, will be removed. We don't want that, so select that and selecting C40 material, thickness is 1 meter for the abutment, and say -1 meter 5 times, so that will generate a 5 meter abutment with 1 meter divisions, and apply. So that's the abutment generated. Now we will create the strip footing below that. So create elements, and we will select C40 again and select strip footing, and just connect the 2 points like this, here and here, and let's see from the hidden view. So I'll click here, and now you can see that the thickness and the strip footing is visible. If you are not able to see the thickness for the plates, then probably your one of the options is checked off, you can go to display option here and go to draw and make sure that both these options are checked on, frame thickness and plane thickness. And once it is on, you should be able to see the thickness as well. Okay, now the next thing is the crosshead and the piers over this location. So I will again switch off the hidden view, go to the top and zoom in and select the central diaphragm here. Okay, and now I will copy this diaphragm downwards. So I'll say go to node element and say translate and copy this in the Z direction -1.7 and apply. Let's check. So that's copied here. Now I will create, but remember this is I copied the central diaphragm, so that means this is also a central diaphragm section, you can see from here, but we don't want that, we want a crosshead. So I will just select this these elements and go to the works tree here. If you are not able to see the tree menu on the right, then you can bring in the tree menu by right clicking on this black part and say tree menu 2, and then you can go to works here. So normally your dialog boxes will open on the left, and the other tree menu options you can access by getting the tree menu 2 activated. So I've selected this section and now I'll drag and drop crosshead, and you can see the difference now. Okay, so let's mark the points from where we'll drop the columns. So I'll just use this node and say translate, copy, and just enter the distance. So let's say Y direction, and that's 2.1 meters, and say intersect frame elements and apply. So we have a new point here, that point will be the column location. Then do the same thing for the other end, this time -2.1 and apply. Then we go to extrude, node to line elements, C40 and Pier column, and enter the distance. So that's -5 meters. Let's say keep it 4 meters, and we'll use these nodes, this one and this one which we just created, and say apply. Let's check from the hidden view whether we have got the section dimensions correctly, and yes, they are entered correctly. So now the sections are all in, materials are properly assigned, so we'll start applying the boundaries to the structure. So switching off the hidden view, we can see clearly that there is a gap, though visually by rendering it seems that the sections are well connected, are just in contact, but we have a gap here. These elements are hanging in midair, so we need to connect them rigidly. So for that purpose I will use the function of rigid elastic link. So select go to boundary, elastic link, and make it rigid, and we'll just connect node to node. So start by this member, this node here, and just drop in more number of nodes, more number of links. Okay, so between this and this, just a minute. Yeah. Okay, and here again. Okay, so in order to apply the links, I'll just activate the member at the center, so it's easier to assign that way. So I've selected and activate, and let's just display the links we have applied till now, and now we can easily select and create the link. So that's done now. We have made the crosshead to be rigidly connected with the central diaphragm. Now we activate the entire model again, and we apply some supports at the column bases and also supports to the abutments. Okay, now let's start with the pier columns first. So go to define supports, and the pier base, select the nodes here and say fixed in translation, fixed in rotation, apply. Then we will apply some boundaries to the abutment. For applying boundaries at the abutment, we need to be sure that we are applying the boundaries in the correct direction. So normally we have the boundaries applied in the local direction of the plates, in the local axis direction. Okay, so let's check the local axis of these plates. We can check the local axis from display element local axis. Click OK, and let's change to the front view, and you will see that the local axis of these the abutment elements, they are in the same direction. See, so this may lead to wrong assignment of soil pressure or boundary conditions, because we want the soil pressure to be applied in the opposite direction for both these plate elements, and you can see they are all both of them are oriented towards the same direction. So what I'll do is I'll just select the abutment over here and go to node element, change parameters, and say reverse element local, and apply. So that will reverse the local axis of the plate element on this side, or the abutment on this side. So now I can start by defining the boundaries. So I'll check off the local axis display and go to boundary, integral bridge, and select the abutment spring. Direction is normal to the plate. Element list, so that is the elements which constitute the abutment. So I'll select all the elements here. Select nodes for the footing, so for the strip footing I select the nodes here, and now I'll enter the height of the abutment. So just click on the 2 points like this to enter the height. Abutment width, click like this. And deck length, so we have the deck length here, and then void ratio, so we entered the void ratio, and thermal expansion allowed in this maximum differential thermal expansion allowed in this bridge, so that's say 20 degrees Celsius. If you're not able to see your units in Celsius, you can always change them from tools, unit system, and make it Celsius. Okay, material is generally C40 for the deck, and For the strip footing, we'll apply some foundation width, which is 4 meters, and bearing pressure 120, and apply. So that is applied. Some springs, some compression only springs for the abutment, and some linear springs for the strip footing. We'll do the same on the other side. So unselect all the elements and then select all the abutment elements here, select all the nodes for the footings and apply. Close this. So we have got all the springs here. If you want to change the spring stiffness of any of these springs, you can always right click and go to properties and change the spring constants. If you double click, they will highlight which node they belong to. So as you can see, it's highlighted here. Then you can also check the compression only springs for the lateral direction. Okay, so that's applied. The boundaries are applied. Now we will go to the load application. So we'll start with defining some static loads. So we go to loads, static load cases, and give a name to the different cases. So starting with self weight, say dead load at wet concrete. So wet concrete, this is load which will be used in the construction stages. I'll just define it as a construction stage load. You can also put self weight as a construction stage load if you want to, because then it will only be considered in the construction stages. So I might as well do that. So self weight, add, then we have pre-stress. So pre-stress will also be applied on the tendons in the construction stages. So just say add. If you apply it as a static load, so you just change it to pre-stress type from here. So pre-stress, and that then you can consider it both in the construction stages as well as in just a normal static analysis. Then we have surfacing, which again we will apply in construction stages. So add, then parapet will be like a dead load to the construction stages. So add here, and then we have earth pressure will be applied in the construction stages. Add. So that's it. We have applied most of the loads here. We can also include uniform temperature load if you want to as a static load case. So just change it to temperature, add, and you can add wind loads and other loads, but this is a very small bridge example, so we'll not go for other wind loads or other kinds of loads here. So we'll start with now defining some groups, because when in the construction stages, when you are bringing in different members in stage 1 and stage 2, then you need to assign which group they belong to. So I'll create a group for each type of member. So first I'll start with the substructure group. Substructure group will include of the piers, abutments, the diaphragms, all in one place. So just select the abutment, the diaphragm members here, and the pier as well, and the abutments here, and drag and drop. Then we have if you right click and go to new and add the precast beams. Okay, so all my composite sections will be under this category. Then the parapet, so select parapet 1, press Ctrl and select parapet 2, and right click and select and drag and drop parapet beams. And then we have the transverse grillage members. So transverse, and for this I select the transverse, double click on transverse and drag and drop transverse. Okay, now I will create groups for the boundaries. So right click new, and say in the first in the first construction stage I will use all my soil springs and all the fixed supports in my model. So I'll say all boundaries, and select everything in the structure, all the boundaries, and drag and drop. So it will include all the boundaries in the structure and include them under one group. So when I say I want all boundaries in construction stage 1, then the software will apply the links and supports to different nodes. Now we create load groups for different load cases, starting with self-weight. Then create a group for pre-stress or pre-tension. Create another group for wet concrete. And create another group for surfacing. We have parapet loading. Okay, and we also have soil pressure. Okay, let's go with these cases for now, and later on we'll also see the tendon groups. So let me first apply the static loads. So let's focus on the deck first. So I'll go to static loads, self-weight, select self-weight, and select the load group self-weight and say -1. So that will assume self-weight in the gravity direction. Add. Then element loads, wet concrete, select wet concrete from here, and we select the composite section, so all the composite sections, and enter the wet concrete load. So we can just enter a calculation of that, times 25 the unit weight of concrete. Then we have 0.2 meters the depth of the slab on top, and then width of the slab. Say we also include the formwork as well, so just increase the depth slightly. That will make it 0.25 for example, and apply. So the weight of the slab is now applied successfully. Then we go to the parapet, or sorry, the surfacing load. Make it surfacing, and just repeat the same thing. This time we will input a lesser value of the depth, so say 0.15, and select the composite sections again and apply. So that's the surfacing load applied, and then we have the parapet. For the parapet we will select the parapet beams only, so group parapet beams, all the parapet beams are selected, and assign them a UDL of -10 kN per meter. Apply. So that's the loading for the deck and the parapet, and now we will load the the abutments. So select hydrostatic pressure loads, select earth pressure, soil pressure group, and reference height is the top. The direction is local Z, so local Z of the plate elements. Constant intensity, this is the pressure at the top, which is we can assume as 0 because we don't have any surcharge at the top. Then gradient intensity, this is the variation of the soil pressure with depth. So we'll enter 19 times the active pressure coefficient, and select the soil pressure, select the abutments to apply the soil pressure, and apply. So that is applied successfully on the abutment. Close this, and now we will shift to the uniform temperature. So temperature pre-stress, element temperature, select uniform temperature, initial temperatures is 0, and say final temperature. We can double click on all the composite sections and assign them with 20 degrees, applies, and close. We can similarly apply another uniform temperature case for the cooling. So we can enter -20 in that case, and consider the cooling effect. Okay, now for the tendon profile, for defining the pre-stressing tendons in the precast beam, I'll first go back to the AutoCAD file just to show you how the tendons are arranged and how we will consider in the software. So that's the cross section showing all the tendon arrangements. You can see the cross marks, they represent the tendons in the bridge section. So we have tendons at different levels which are measured from the bottom fiber, 60 millimeters, 110, 210, and going up to 1430 mil from the bottom fiber. So we will use the bottom fiber as the reference, and we will enter the distances as per this drawing. Then we also have the tendons debonded by certain lengths at both ends, so we will use them accordingly. Okay, so in this example I will not model each and every tendon. I'll model a few of them, and then I'll bring up another model where I have already done the tendon modeling. So just to tell you how we will be going through modeling all these tendons. So in Midas we can enter the tendon profile, the end and the start and end coordinates of the tendon longitudinally, and also the tendon offset from the center line of the element in the lateral direction and also in the vertical direction. So we have so many different tendons, we can group them. We can, instead of entering each and every one, we can say enter 2 tendon strands at a time. So we'll enter pairs of tendons at a time. Because the bridge is highly symmetric, we can also go for, we can say that apply 1 tendon at the center, which is 22 times the area of 1 tendon. So we can increase the area of the tendon at any given location and apply the tendon in the center if you have a symmetric arrangement of tendon profiles, which is, we can see in this case it is true. We can apply a large tendon here, which is 22 times the area of the 1 strand, and we can consider that in the analysis. So that will give you the same results as the different tendons in different locations. So let's go back to the software and see how we can model the tendons. So going back to Midas, and first of all we define the tendon groups for different tendon levels. So we define, say, tendon 60 millimeters, Then we define tendon, say 110 millimeters, and so on. So we define different groups. These groups are basically, when we see the results in the after the analysis, we can see the stress loss or stresses in the tendons for a group, so that will give you the equivalent or average stress in the tendons rather than seeing the results for each tendon individually. So the group is very useful for getting an idea about the average loss in the tendons at a given level. So I'll go back to loads, temperature, pre-stress, and tendon property. Add, give the name to a tendon, and we will be doing precast beam analysis. So pre-tension tendon, the material is high strength steel. Tendon area can be selected from this box. We can select strand diameter and enter the number of strands we want for one particular tendon point. So in this case we will apply it manually. So 3.14 pi times the 0.0157 and divide by 4, and the diameter is 0.0157, and relaxation coefficient as per Eurocode will select ordinary tendon, and we don't have any friction or anchorage loss, and when we click OK, so that's the tendon property added. Now we will define the profile of the tendon. So to define the profile, we will try to create we'll try to activate one particular girder and assign the tendons to that particular girder. So I'll just right click on composite section and say active, and even here I'll just select one particular beam and say active. So that's one girder. And now going to tendon profile, add, and select the tendon name. So name of the tendon is say 60 millimeter, and left tendon 1, strand 1. Property of this tendon is tendon 2 tendon, and the group is tendon 60 millimeters. Then assigned elements, so this will define which girder I'm talking about. So I'll just select everything on the display, then select 3D here and enter the length coordinates for the tendon, so 0, and Z value, so that is measured from the bottom fiber, so it's 0.06 or 60 millimeters, then 30.5 meters on the, that is the end coordinate of the tendon, and 0.06 meters. Now we specify which is the starting point of the tendon, so I click here and click on the first node here. Then we define the offset of the tendon in the lateral direction. So as per this particular figure, we are defining for this two tendons here. So we'll take the offset as the distance between the center line and up to here. So that is we can say roughly 660 millimeters. Now you also note that we are doing this for both the tendons at the same time, so we are measuring it from the midpoint of these two tendons. So what I will do is I will enter the typical tendon as 2, so that means the area of the tendon will be multiplied by 2, and we don't have to enter 2 times for each strand. We can include them both in under one tendon, and specify the offset. It's 0.66, and Z offset, this is the offset that we provided for this section. So if you remember, we provided an offset as center top, which is this. So since we are measuring the distance from the bottom, we need to give an offset so that the line is fixed at the bottom. So we just enter -1.7 and we click apply. So there we go, there we have one tendon here. We do it for the other end as well. So R and say -0.66 and apply. So we have another tendon here. The group is same, everything is same. Then we go for this the next one. So the next one in this drawing is this circle one. The circle one represents the bonded tendon, debonded tendon. So that's the debonded length at from each end of the girder, 1500 millimeters, 1.5 meters. So let's see how we can enter it here. Okay, so we change the name, make it typical tendon as 1 because we have only one debonded tendon. Group is the same. We want to keep all tendons at this at one given level under the same group name. Then we enter 1.5 as a start coordinate and we subtract 1.5 from the end, so that will be 29 meters. Okay, and we change the offset, so the distance from the center line for the debonded tendon, it's 0.6 meters, and we click apply. So that's another tendon modeled here, that's the debonded tendon. Then we change the name, make it L2 and change it to plus 0.6, apply. So we got another here. Similarly, we can add the other set of tendon, that's 3, and we change it back to 0 because this is the normal tendon, not the debonded one. So using full length of the girder, and typical tendon is 2, so we are entering again a pair of tendons. This is just to reduce the time in adding tendons, otherwise you have to add each and every strand. So you can activate 2 at a time. So this one is 0.52 meters from the center. Apply. Create another one for the other end. Same, -0.52. Apply. And we have another debonded tendon. That is R4. We make it 1. And this time it is 5 meters and 25.5 from the other end, and the Y offset is -0.44. Apply and repeat it for the left hand side, plus 0.44 and apply. So we can keep on adding other tendons. So for the next level, say 110, we can add say 22 tendons at the same time. Let me just quickly do that. So I will change the group to 110, change the name as well, make it 110 and 0. We don't have any debonded tendons for the level 110 millimeters. 5, and number of tendons is 22 as per this drawing here. So we can enter 22 tendons and center them here. So going back to the model, 22 group is 110 and Y offset is 0 because it's at the center line, and we click OK. Sorry, I didn't change the Z offset here. It should be 0.11 here, and click OK. So now that gives the correct location of the tendon. So like this we can keep on adding tendons in the different webs as well. So for the webs we add one web at a time. So and then just change the offset value in the lateral direction and create another one on the other web, and thus we keep on adding the tendons. Okay, now I will take you to the model where I've already added all the tendons, and then we can start modeling. We can start seeing how we can copy those tendons to other precast beams. Okay, so this is the model which is completed with all the tendons for one particular girder. So I will just activate the composite beams and change the view, and we can change the display type to profile point. That's how the tendons look like. Okay. If I go to the top view, you can also see the debonded tendons. So these are the tendon endpoints, these points, and you can see some tendons start from the midway and not from the ends. Those are the debonded tendons. Okay, so now I'll copy these tendons to the other precast beams. So before copying, we need to renumber the elements, since tendons are always referenced with respect to elements. So for copying them, if you renumber the elements, it's very easy to copy the tendons directly by entering the element number or the number of elements to be incremented for. So that's using the element numbers we can copy the tendons very easily. So to renumber the elements, I'll go to the element renumber option, renumber element ID, select all and enter the start element number. So let's say start from 1000, because this element number may not have been used by any element till now, because we have total number of elements as 600. But it's always good to have a check, so you can just right click here and go to tables and see the last element number. So that's 638, so we can safely go for anything over that. So let's start with 1000, and we can give an order for the renumbers, say order as per XYZ, and just select all and click apply. So now the element numbers have been changed. Let's check. If I go to switch on the wireframe view and display the element numbers, and I can see they are 1000, starting from 1000, and they are arranged like this. So there is always an increment of 1 for the corresponding y direction girder, and also here they're arranged properly. So now let's copy the tendons. So I close this and go to loads, temperature, pre-stress, and tendon profile. Select all the tendons by pressing the first one and then shift and last one, and then go to copy move and say element increment. So if you want to copy from this girder to this girder, the element increment is 1 for the corresponding element. So 1, and click OK. So that's copied. Again go to copy move, this time press 2, click OK. Now here if you see, the element number is 1096, whereas here it is 1000, so there is an increment of 96. So you can just say copy move, say 96, and click OK. Let's check here, this copied. Copy move, enter 97, click OK, and copy move, enter 98, and click OK. So all the tendons are now copied. Let's check by switching on the tendon profile point. Okay, just and now I'll switch on the tendon profile point, and let's switch on the hidden view as well. Now you can see that the tendon profile is displayed. It's same for all the precast beams. The next step is to apply the tendon pre-stress, the pre-stressing jacking force to these beams. So tendon pre-stress, and select pre-tension load, select pre-tension load group, select the tendon, so press shift and select the last one. Then we want to jack it from both ends, so both ends, and the applied pre-tension stress we can check. So I will see the area of the tendon from here, so copy the total tendon area, copy, and the applied pre-stress force is can be referenced from the AutoCAD file. That's 209 kilonewton. So I'll just include 209 divided by the area which we just copied, and copy the same thing here. C, paste, okay, and add. So that's pre-stress has been applied to all the tendons. So now I'll close this. So let's start the modeling of the construction stages now. We have created the groups already, and we can start the construction stages. So basically we'll keep the things simple. We'll construct it in 2 stages. First stage we'll have the precast beams with abutments, piles, and abutment piers and all the substructure there, and the formwork, the wet concrete load of the slab acting on the precast beams. Then we can also in the second stage make the section composite, and then we'll keep a third stage for the long-term creep and shrinkage effects for the loss calculation in the tendons. So first of all, since we're talking about creep and shrinkage, let's define the creep shrinkage properties for the concrete. So go to properties, creep shrinkage, add, and we'll select Eurocode, enter creep, enter the strength of concrete, so that's 50,000 kPa. Notational size doesn't matter, we can enter any notational size, the software calculates it automatically. Age of concrete at the beginning of shrinkage, this should be the age when the shrinkage starts occurring, that is when you stop the curing. And then show result, this will show you the creep coefficient and shrinkage strain curve it will follow. And click OK, close. Then we'll define a strength function. Strength of concrete varies with time as well, so strength, and select Eurocode, mean compressive strength of concrete, which is FCK plus 8, so 58,000. Redraw, and that's the strength function of concrete that will be followed in the analysis. Click OK. Then we'll link these functions with the concrete, so select creep and strength function, and we'll link them with the C4050 material, that's concrete, add, and close. So let's define the construction stages now. So we go to loads, construction stage, define construction stage, and add. So first stage is stage 1, say duration is 28 days, let's say it's 7 days, and we include in this stage all the precast group members, all the substructure elements, all the parapet elements, and also the transverse elements. So add them. Now for the precast members, we need to specify the age at which we are applying the pre-stress. So then it will take the correct strength of or the correct strength of concrete as per the pre-stress applied. So I'll just change it to 7 days and modify. Okay, just so that you don't confuse between this 7 and this 7, I'll change this duration to 10 days. And for the others I don't need any age because I'm not considering any creep or shrinkage for them. So go to boundaries, all boundaries, add loads. We have self weight, pretension, now we have parapet, surfacing, and soil pressure acting on the first day. I'll just remove surfacing, we will add surfacing later on. So just say add. Now the wet concrete load also starts acting, so that is say starts acting on the 3rd day for instance. So we can add a day here and say add and include wet concrete on the 3rd day, add, and say save additional step result. So it will save the results of 3rd day and 1st and last day as well. So click apply. That's the first stage added. Stage 2 is the stage when concrete is poured and when the deck becomes composite with the girders. So in this stage we don't add anything new, just we add surfacing on the last day. So on the last day of the construction we add surfacing. I just delete the intermediate step, we don't need it for this stage. So for the last day we have surfacing, apply, and then we have stage 3 which is long term stage. So I'll just name it long term and change the duration to 1000 days just to see the long term effects, and nothing new to add here. So I'll click just OK. So let's review the stage 1 and see what we have done here. We have activated basically everything. We have the formwork in place, we have the transverse members which represent the formwork and the wet concrete, the slab in the transverse direction, and we have the parapet beams which include the edge parapets, and then we have substructure which includes the piers, the abutments, the diaphragm members, everything. Then precast members which are the W11 beams. Then we have boundaries which include soil springs, rigid links, and the fixed supports of the piers. Then in the loadings we have every type of load, self-weight, pretension from the very first day, soil pressure, wet concrete, etc. So that's it. Close this. Now we will differentiate and tell the software that which part in the composite section will be activated in which stage. So I'll click on this option and say add and go to stage 1, select composite beam, and you can see part 1 and 2. Part 1 is the W11 beam, part 2 is the slab. So I'll select material, get concrete or C5060, whatever you have named it. Stage 1, age of the girder at the time of activation in the construction stage. So we activated it with the age of 7 days. So type in 7 here, then material and say deck, and stage 2, that's when the deck comes into action, and we select 10 days, sorry, 7 days for the deck as well. H value for creep and shrinkage is automatically calculated, and now you can click. So if you want to modify say the stiffness of the members, if you want to assume a cracked stiffness, then you can change the stiffness from here. So you can enter any you can change the stiffness scale factor, so you can enter some scale factors here and reduce the area of a given part, deck or the girder. So now click OK. You can enter creep shrinkage for the deck as well, but I have not entered it here, just to consider it for the precast beam only. So that's the construction stage modeling. If now we can check the different stages. So stage one has the has everything in it except the composite section, the concrete deck. Stage 2 has got the concrete deck in composite section in it, and long term has everything with an added time scale. So I'll go to base stage again, and now we will see the live load application on this bridge. So that comes under the moving load option. You can select the Euro code from here and apply lanes, traffic lanes on this bridge and some vehicles, and do the live load analysis. So for the live load analysis, the first thing for a village model is that we create a group that has all the cross beams in it. So I've already created a group that contains all the cross beams. Just change back to initial view, yes, and now double click on cross beams. That shows the cross beam members that I have included in this group. So you need to include all the cross beam members, the Y direction members, under the cross beam group. Then we can go to traffic line lanes and start defining the lanes. To keep it easier, make it easier in assigning the lanes, I will only activate the deck. So what you can do is go to view and select by plane and select only the deck and select active, so only the deck is active. And now we can create the lanes here. So I go to loads, moving load, traffic line lanes, add, and enter footway 1, eccentricity minus 0.75, wheel spacing as 1.5, and lane width is 1.5. So again, I'll just to remind you, I'll open the AutoCAD drawing and show you the lane, how I'm going to define the lanes. So that is 1.5 meters the footway. Then you have 3 meter lane A, and then 3 meter notional lane B, and then another 1.5 meters here. So keeping this in mind, I'll try to assign the lanes. Vehicle load distribution is cross beam type, so select cross beam and select the group that includes all the cross beam members. If you have a skew in the bridge, you can enter the skew angle here, so the lanes will also be skewed. Now we just mark the points, select point 1, point 2, and apply. So that's footway 1 added. Then we select lane A, and we keep the eccentricity as -3. Wheel spacing as per Euro code is 2 meters, 3 meters is the lane width. Delete the previous information and again select the points and apply. So that's lane A, and then we do that for lane B as well. Change it to -6, delete the previous information and create the lanes again and apply. Then last one is footway 2. We don't have any remaining area for this bridge, so I'll exclude the remaining area definition, 1.5 and 1.5 here, and delete the previous information and define the lanes here and click OK. So that's all the lanes are now defined. Now we will define the vehicles to run on these lanes. So vehicles, add standard, start with road bridge load model 1 and enter the adjustment factors as per UK National Annex, 0.61, 2.2, 2.2 and 2.2 here, and apply. Then we have load model 3 UK National Annex, which includes SV196. We'll just change the name to SV196 and apply. Then we have footway bridge load models, uniform footway, so 5 kN per meter square. As per the National Annex, we need to take 0.6 times the footway loading, so 0.6 for the group 1. So just change it to 0.6 times. click OK and close this. And now we go to moving load cases and combine the load cases. Add, say, load model 1 plus footway, that's the group 1 combination. Uniform bridge footway, we don't want to include psi factors for this, so I'll just ignore psi factors. Bring all the lanes under the selected lanes category and keep the footway lanes under the footway category and apply. Then we have load model 1 plus load model 3. Select straddling, so this particular vehicle, load model 3 special vehicle, can straddle between lane A and lane B. This time we will not ignore the psi factor, we'll consider psi factor for load model 1. Select SV196, lane A and lane B in the straddling lanes category and click OK. So let's go for these two combinations. We need to select other combinations as well as per this table in the national annex of Eurocode. So it says we have done only group 1A and group 5 combination till now, so we need to create other combinations as well, but I will skip this for the today's this presentation. So let's go for the only two combinations. Okay, so here we are. We have modeled the construction stages, the live loads, and now we are ready to do the analysis. So we can run the analysis from analysis and perform analysis, which is this button here. So we can click on this. Okay, so the analysis has now been completed, so we can now look at the results. So in the results combinations, we can create some load combinations for, say, the concrete design. Some of them are already created here. I'll just delete them and maybe create new combinations, auto generate, and say Eurocode, and we can select the different load factors and click OK, and the combinations will be generated for strength or serviceability. We need to be careful in the combinations as well, because we can select construction stage only or static plus construction stage load cases. So since most of our loads are included in the construction stages, you should go for construction stage only and click OK. So that will include the dead load, which includes all other load effects that we included in the construction stage: creep, shrinkage, tendon, that is pre-stress, and load model 1 or the other load models can be included under the serviceability or strength checks. We can create our own combinations by typing in the names, say combination, and say strength check, and we can add, say, self weight, we can add pre-stress, and say let's say we can add the earth pressure as well, and we can add LM1 plus LM3. So we can give different factors to them and consider them in the design or the analysis. Let's look at the results. So let's see the Pier reactions at the bottom of the Pier. Reactions, we can select load case, say self weight, values, and apply. So that's the reaction at the Pier, and you have some reactions also in the for the abutment. Then we'll look at displacements. So we'll see stage by stage displacement. Stage 1, switch to the hidden view. Let's look at the deformations. Apply. That's the deformation in the structure. We can look at the different deformation for dead load, deformation due to dead load, deformation due to um, all effects, deformation due to pre-stress. Okay, and we can check the long-term deformations as well. That's the long-term deformation. You can see the values here. You can make the legend to be fixed so it's more readable, changing it to millimeters. So that's the deformation value due to pre-stress, due to summation. That's the deformations due to the summation, 27 millimeters. Then we will check the force results. So let's go to long-term forces beam diagrams, and we will focus on the forces. So let's see the beam diagrams here. So I'll just turn on the switch of the deformed shape. That's the bending moment in the precast beams. We can also check the bending moment separately in the concrete girder and the slabs. So if I say part 1, which is concrete girder, precast girder, and say apply, that's the bending moment in the precast girder. If I say part 2, that's the bending moment in the concrete. Then we can check stresses. So if you want to see beam stress diagram, go to beam stress diagram and select a particular part, say part 1 or 2, and select part 1, which is the precast girder, say combined axial plus bending, and we can select the points for generating the stresses. So let's say bottom flange or the bottom flange of the W beam, select 4 as per this figure and say apply. So that's the stresses in the bottom flange. You can see mostly they are the negative stresses in the bottom flange. Then we have part 2. We have got some stresses here. Part 2 is the concrete. So if I just say stress point 1, 1 means the top of the concrete slab, and that's the stress diagram. And we can also look at the results for the moving loads, live loads. So let's say I go to post construction stage and select a live load case, say load model 1+3, and select forces, beam diagrams, say apply, solid fill. That's the envelope of the force diagram, the beam bending moment diagram. And we can also create the check out the maximum or minimum element. So we can select a maximum element, bending moment for the maximum bending moment is the element number 1055. So we can go to moving load tracer and beam forces moments and type in the number of that element 1055 and select load model 1 and 3, and we can see the vehicle position causing maximum bending at this location. That's the vehicle position. You can zoom in and you can see the results here. Now if we were to design the we can extract the results for bending moments and shear forces in the sections using result tables. So any type of results can be extracted from here. We can go to beam force and stress, and we can select a load case and see the different components of the forces here with the element numbers noted here. The most important thing about the precast bridges, pretension tendons, would be to check the losses. So we can click on tendon loss graph and see, select a particular tendon, and we can see the variation in the tendon force with distance. So I'll animate it, and you can see the result variation, how the force varies in the tendon profile. We can also get a tabular report showing the different loss components. So tendon loss, so we can select a particular group from here, like tendon 60 is selected over here, and we can select a stage from the stage selection box. And that will give us the stress, the tendon stress loss, and we can check the tendon force loss as well. So force after immediate loss in the when we pre-tensioned the tendons was 180. We applied 200 kilonewton as the force, and then we had creep losses, relaxation losses. Okay, so that's how we can check the results for different force components in the bridge. We can also design some of the members, like if we want to check the reinforcement for the concrete piers, we can enter some value for the reinforcement, say column section data for checking. You can enter some ties arrangement, and say we can enter the rebar values, 20 millimeters and 20 here, and for position 2 enter 5, 20 here, and we can enter for position 3 as well, 5 and 20 here, and that's the clear cover 0.05. That's how the rebars will be added, and cancel, and we can say concrete code check, column checking, and that will run the design for the columns. We can see that's in blue, that means it's passing the check based on the rebars we have entered. We can select the column here and say graphic, and that will give us a summarized report for the column, and we can draw the PM interaction curve for the reinforced concrete design, and we can select a particular column out of them, so one of them, and click on detail, and that will give us the detailed step-by-step calculation report. So that's the workflow for the design of the modeling and analysis of the precast bridges. One thing I would like to mention here is that the results that you obtain from this example, they may not be the accurate results for the example, because this is just a demonstration. For the correct results, we should always check whether our section properties and materials are properly applied to the structure, and then we should see the results, and then we should be able to get the correct results. So that's basically the conclusion of this presentation. We saw how to create an AutoCAD, how to bring in a section from AutoCAD, how to assign tendons to it, how to define construction stages, creep properties and shrinkage properties, and then how to design a simple column. And then we can just use these member forces. So for the composite section, we get the part-wise results in a table format. We can take it from here and select, say, self weight, and we get the results for composite section part wise, part 1, part 2, that is beam and the deck, and then we can include them when we're doing the design check and see the results. So that's it for now. You can stay tuned to our YouTube channel Midas UK to gain access to other types of bridges and how to model them in Midas and look at the design forces and carry out the design. So thank you for listening, and bye for now.